Welcome to the presentation of the REWIRE Attestation Engine. I'm Stefan Vasiliadis from UBITECH, and I'm going to be presenting you the attestation capabilities that each REWIRE-enabled edge device is envisioned to support. Our main focus is to design and implement sophisticated mechanisms that ensures the secure life cycle of an edge device. To this end, we enable the trust assessment of an edge device by exposing interfaces for advanced attestation protocols in order to provide verifiable evidence over the device's trust state. Our main focus right now is the trust aspect of integrity, but we are aiming to expand our functionalities to also include others like safety and resiliency. To this end, we are targeting the attributes design time integrity and boot up integrity that are characterized by the static properties of the system, as long as runtime integrity through constantly introspecting the execution of safety critical applications. As in REWIRE, we are moving towards a zero trust model. Our schemes are zero knowledge attestation schemes, thus the prover is not disclosing any information regarding its configuration state to the verifier. Finally, it has to be noted here that we support secure software updates whilst ensuring that no obsolete key restriction usage policy is enforced. The innovation of REWIRE comes from employing local attestation through policy-restricted attestation keys. During runtime, by leveraging real-time tracing, the attestation engine of REWIRE shall enforce a predefined set of policies, and if and only if the whole set of policies is enforced successfully, the device will provide valid attestation evidences. All these are possible with the REWIRE's Trust Computing Base that is equipped with a trust execution environment, specifically Keystone. REWIRE's TCB exposes Trusted Device Interfaces, TDIs, that enables a hardware-based and secure key management system, a key restriction usage policy verifiability mechanism, and of course real-time tracing regarding the configuration of safety-critical applications as long as the flow of execution of such applications. So, let's take a deeper dive to the components that make all this possible. We have the domain manager, which is a trusted third party that manages the secure onboarding of each device that wishes to participate in the REWIRE infrastructure. We have the attestation agent that exposes the trusted interfaces for providing authentic traces and ensuring the secure communication of these measurements. We have the verifiable policy enforcer, which basically is responsible for verifying that the latest deployed key restriction usage policy is associated to the correct static properties of the target application. And finally, we have the tracer, which is responsible for continuously monitoring processes and routines that are executed in the untrusted world. Having described all the involved components, we can now proceed to a high-level overview of the attestation algorithm. To this end, we identify two distinct phases, the join phase and the runtime attestation phase. During the join phase, the attestation agent is launched and initiates the secure onboarding, so as to eventually fetch from the domain manager the key restriction usage policy under which the attestation key will be bound. The domain manager injects to the verifiable policy enforcer the VPE key and finally constructs the authentication ticket to be used by the attestation agent during runtime. For the runtime attestation phase, we consider a verifier that challenges a prover to provide attestation evidence for each configuration. The prover initiates the configuration integrity verification protocol for all requested services. Eventually, the prover responds to the verifier with a digital signature, and the verifier goes off to verify the configuration state of the attested device by verifying the digital signature provided by the prover over the challenge. With all the necessary information provided, we can now proceed to a demonstration of our actual implementation of the attestation scheme. For this demo, we are using a chem emulation of a RISC-V Ariane operating system that is keystone enabled. As you can see, the supposed device is launched and sets up the security monitor with the physical memory protection capability that the RISC-V architecture offers. We proceed with loading the keystone driver to the kernel and eventually executing our protocol. For this demonstration, everything is executed within the same enclave. Unfortunately, we can't get log messages before the execution is over, as everything is executed in the trusted world. Now that the execution is over, we can actually see every step of the execution. First of all, the domain manager calculates the key restriction usage policy to be enforced for the attestation key. The attestation agent creates the attestation key in respect to the issued key restriction usage policy. The domain manager then initiates each operation that is relative to the join phase and calculates the policy that is to be enforced for the VPE key and eventually creates the VPE key. The VPE key is then injected inside the verifiable policy enforcer enclave, and finally the domain manager calculates the authorization ticket for the attestation agent, thus completing the join phase. Then we can see that a verifier comes and challenges the prover's attestation agent. The attestation agent then pings the tracer to collect and sign traces for the security critical applications, and then we see that the verifiable policy enforcer checks that both the software version of the tracer and the attestation agent is the expected one, and then the attestation agent goes off to enforce its own key restriction usage policy, and if this is completed successfully, which in this case it is, it creates a digital signature over the challenge that the verifier issued. Finally, we can see the signature and the public key of the attestation key that was used to create the digital signature, the attestation evidence. Closing this presentation, we separate the future steps to two categories: short-term and long-term. For the immediate short-term future steps, we plan to finalize the implementation of the monitoring hooks, finalize the instantiation of each use case, and eventually perform a full-fledged evaluation benchmarking of the attestation schemes for the deliverable D6.1. As long-term future steps, we plan to implement the described multi-layered certificate protocol, implement the key management system as part of the security monitor, which is now just inside the enclave, integrate the attestation as part of the zero-touch onboarding as described in the deliverable D4.2, and finally implement and finalize the design of the sign encryption scheme that we described in deliverable D4.2. Thank you all for your attention. That's it from my side for the presentation of the REWIRE's Attestation Engine.